Good morning, everybody. Well, we're finally starting Chapter 4 on dynamics. We're going to be looking at forces and Newton's laws of motion. These are the things that help us explain motion. Now, it happens to be one of the biggest chapters in the book, so we'll be taking it parts at a time. Obviously, there's no way we can go over this many pages of notes in one go. So we're simply going to be looking at Newton's laws today. Now, the first thing we need to do is define what a force, which is always denoted by a capital F, what a force is. And it is a vector quantity. Think about it. There's absolutely no way you could apply a force and have it not be in a direction, because a force is a push or a pull. And whenever you push or whenever you pull something, you have to pull in a direction. There's no way you can't pull in a direction or push in a direction. And this will affect the motion of the object. Now, the unit of measure for force is the Newton, named for, obviously, Sir Isaac Newton. We use a capital N at the end of the measurement, and it is a derived unit. In fact, 1 Newton of force is equivalent to 1 kilogram times meter divided by second squared. This is the combination of base metric or base SI units that the Newton is made up of. Now, there are 2 ways to categorize forces, and these would be field forces, which are non-contact forces, okay? These are non-contact forces, such as gravity, magnetic force, and electric force. These forces do not have to have the objects physically in contact in order for the force to exist, which is kind of lucky for us, because if gravity was a contact force, that would mean the sun would have to touch the earth to exert its gravitational force, and then the earth, well, we'd be vaporized. So, good thing that it is a non-contact force. Magnetic forces, a magnet, one of the magnetic poles on a magnet does not have to physically touch the earth in order to be affected by the earth's magnetic field. So, forces like these are non-contact forces, but they're also called field forces because they generate a field of force around the object. Okay? We'll talk more about that later. Then there are the contact forces, where the objects actually must physically touch in order to exert the force. Forces like applied forces from people or animals or animate objects like a tractor or a train. Friction force between surfaces. Normal force also exists between surfaces. It is a surface pushing back. Tension force in a string, a wire, a cable. We'll be looking at all of those forces. Now, whether you're looking at one or more of these forces, all of the forces, individually or in combinations, affect the motion of objects according to 3 basic laws developed by Isaac Newton. Now, Newton's first law of motion. Newton's first law of motion. Okay, this is sometimes also called the law of inertia because it has to do with the inertia of a body. Now, I don't know if you remember, but inertia is basically the property of matter that resists any change in the state of motion. So, if an object is moving, it wants to continue moving because its inertia wants it to. If it's at rest, its inertia wants it to remain at rest. And it resists changing that. Now, that doesn't mean you can't overcome the inertia and change the motion. It just means the inertia of a mass will always resist any change in the state of motion. Now, Newton's first law of motion is directly tied to this. Notice the 3 parts or three parts of this. It says a body at rest stays at rest. So if it's not moving, it wants to stay not moving. It says a body with constant speed stays at constant speed. So if you're traveling down the interstate at 50 miles an hour, your car wants to continue moving at 50 miles an hour because of inertia. And this will happen. A body at rest will stay at rest, and a body at constant speed will stay at constant speed under one condition: as long as the net force acting on the object is zero. Now, what is a net force? A net anything is the sum of things. So a net force is the sum of all the forces. Now, if you have a part-time job, you know what net pay is. It's the pay that you take home after all of the bonuses and all of the withdrawals are taken from your gross pay. Okay, like they have to take out for taxes and Social Security, but you might have earned some overtime, so that would be added in. So after you add up all the little pluses and minuses, you get your net pay. Well, after you add up all the forces in the different directions, you get your net force. And if the net force is zero, then the body that's at rest will stay at rest because there's nothing to overcome the inertia. The net force is zero. There's nothing to change it. If the body is moving at constant speed, it will maintain constant speed. Because the net force is zero, there's nothing to change the motion. There's nothing to overcome the inertia. So, basically, we're saying that the object is in a state of equilibrium. All the forces balance out to a value of zero. Now, that doesn't mean that they physically disappear. The forces aren't disappearing if they balance out. If you have one pointing one way and one pointing the other, and they're opposite directions but the same magnitude, we know from collinear vector addition that the sum of the two would be zero, but that doesn't mean that they don't exist anymore. They do physically exist. They're acting on the object, but their mathematical sum is zero. So, what we like to do mathematically is we say the net force is the sum of the forces. Now, here's that Greek letter sigma that in math class is shorthand for add 'em up. So this says the net force is the addition or the sum of all the forces, whatever you've got. And if that sum is zero, then there's nothing left to change the motion. In other words, there's nothing left to produce an acceleration. So the acceleration is zero. Okay? All right, so real quick, remember that the Greek letter sigma means mathematically to summate or to add together. If you don't know that, now you do. It's shorthand. Okay? All right. And anytime an object is in a state of equilibrium, this has to be true. The net force has to be zero so that there's nothing left to overcome the inertia and change the velocity, change the motion. Okay, so right here, let's fill these in. It should say the net force is the sum of the forces acting on the object at the time that you're looking at. When the net force is zero, the forces are physically sustaining the existing motion. But there's nothing left over from the sum to change the motion. Okay? So remember, the forces are mathematically canceling out. They're not physically canceling out. They're still acting on the object because they maintain any existing motion as a constant motion or as rest. But they're still physically there. All right? All right. Now, let's talk about Newton's second law of motion for just a minute. Newton's second law of motion. All right? Now, Newton's second law of motion is what happens when the net force isn't zero. What if you add the forces up and there is something left over? Okay? Well, when there's something left over, when there is a net force that is not zero in value, it will make the mass of the object accelerate or change motion. Okay? Now, when the object changes motion, when it accelerates due to an unbalanced force, a net force, they don't all balance out anymore. You have something left over. Then the object is said to be in a state of non-equilibrium. And mathematically, that means when you sum the forces, the net force is the sum of the forces. When you sum the forces, whatever's left is going to make the mass of the object accelerate. So, Newton's second law is Fermat. I like to say that. Newton's second law is Fermat. The net force, whatever value it is, will make the mass of the object accelerate. Okay? And for the same net force, bigger masses produce less acceleration. All right? But if you keep the mass the same and change the net force, the acceleration will vary as the net force. If you increase the net force, you get a bigger acceleration. Decrease the net force, you get a smaller acceleration, as long as the mass stays constant. Okay? Now, real quickly, I want to talk about, since we're looking at these forces, oh, and I meant to do this too. Put a little thing there and a little thing right there. Okay, so those two go together. Non-equilibrium, the mass will accelerate. Equilibrium, the mass is at rest or constant speed, constant velocity, because there's nothing to change it. Now, since we're talking about forces, we need to talk about the forces acting on an object and the forces acting from an object. So let's talk about this. The first one we call external forces. The net force that acts on an object is made up of external forces. Forces that are acting on the object from other objects. Okay? Forces, however, that act on one part of an object, from one part of an object on another part of the object, are not external. They are called internal forces. To give you an example, let's suppose we look at a wagon filled with bales of hay. And let's say the wagon is going to be pulled by a tractor down the road. Okay? So, if we look at the wagon and the bales of hay as our object, the tractor pulling on the wagon with its bales of hay exerts an external force. Okay, so the pull from the tractor acting on the wagon and the bales is an external force. But if we look at the force of between the pressing force between one bale of hay and another bale of hay, or the wagon supporting the weight of the bales, pushing up on the bales, since we're considering our object to be the wagon and the bales, those pressing forces would be considered internal forces, okay? And they don't affect the motion of the wagon. They're not part of the sum, the net force, that either keeps the wagon at constant velocity or makes it accelerate. Only external forces change the motion of an object if it's unbalanced. Internal forces have nothing to do with changing motion. So when we look at these two formulas, the first law in a state of equilibrium and the second law in a state of non-equilibrium, the net forces that we're talking about are external forces always. They're not internal forces. Okay? So that means defining the object that you're looking at or focusing on is rather important. And we'll be discussing more of that. Now, obviously, since forces are what change the motion, and we've already learned how to describe motion, we should be able to use what we've learned about changing the motion with our linear kinematics. That is, using the second law with our linear kinematics. So let's take a look at this example where we're going to use the dynamics, the second law, with our kinematics that we already know. Here we have, in a baseball game, a pitcher throws the ball, and look right here, we're given information, I'm just going to underline it first, with a velocity of 30 meters per second toward the batter, who strikes the ball, a bat. I think that's supposed to say with a bat. Who strikes the ball with a bat and sends it out over second plate with a velocity of negative 32 meters per second. Determine the net force exerted on the ball by the bat. Okay, so let's take a look at what we know. All right? First off, kilograms. Now, that's not a kinematics measure. Kinematics measures are meters, seconds, meters per second, and meters per second squared. This is a dynamics quantity. It's the mass of the object. Okay, so the mass is 0.5 kilograms. Now, when the pitcher throws the ball, he throws it toward the batter. And when the batter hits the ball, it goes back out over the pitcher and over second plate with this velocity. And notice the direction they give it. They're saying that back out over the plate is negative direction. So toward the batter is going to be our positive direction. Okay? Now, what else do we know? Well, we are going to determine the net force acting on the ball. All right, the net force. So let's think about this a minute. Almost forgot. I forgot to write these down. If the pitcher throws the ball first, this is going to be the initial velocity, and then the batter hits it, so that's going to be the final velocity. Okay, sorry about that. I forgot to write those down. Okay, and it just dawned on me, there is a piece of information missing. I can see it on my key, which you all aren't looking at, but one of these days I'm going to get around to adding that in like I should. But the time that the bat is in contact with the ball is 0.05 seconds, and we're going to need that. Okay, so that's the time that the bat is in contact with the ball, because that's when the motion of the ball is going to change from 30 in the positive direction to 32 in the negative direction. So that time period, even if it is very small, is when the acceleration, the change in motion, takes place. So that's when the net force acts on the ball. Okay, let's see what we need. We want to find the net force. Well, right now, we only have one formula that we can use with net force when motion changes. That's the second law. So we know that the net force is what makes the mass accelerate. And it's the net force that we want to find. But, oh, wait a minute. We got a problem. We have the mass, but we don't have the acceleration anywhere. However, we know kinematics. We know how to use kinematics to find an acceleration. Now, we know v sub f, v sub o, and t, the time of the acceleration. So the best formula to use here would be the definition of an acceleration. So before we can find the net force, first we have to find the acceleration. Okay? And there's the definition of acceleration right there, and that's all we need. Now, if you want, you can either find the acceleration separately and then stick it into the dynamics, or you can do what I like to do to save a little trouble. I like to simply substitute one formula into the other. So we get this. Okay? All right, now, if we do it this way, then we're going to get that the net force equals 0.5 kilograms times negative 32 meters per second, because that's the final, minus positive 30 meters per second, that's the initial, over the time period through which that changed, so 0.05 seconds. All right, so far, so good, right? Okay, so notice we're going to get meters per second divided by seconds, which is meters per second squared of acceleration, and then kilograms. So we're actually going to get a kilogram meter per second squared, which is a Newton. So we're doing okay. Now, if you stick that into your calculator, you'll notice you'll end up with a negative value. In fact, you end up with negative 620 newtons. This means the force that acted on the ball acted in a direction back out over the pitcher's mound and second plate, which makes sense because the bat is headed towards the ball when the ball is coming towards the bat. Since the ball was in the positive direction, the bat has to be swung in the negative direction to strike it and push it back the other way, changing its velocity. So it makes sense that the force from the bat is negative, okay? All right, now, so we've learned how to use our kinematics in association with our dynamics. In fact, if you'll look, the only link between kinematics and dynamics is right here. It's the acceleration, and this is actually very important, so we're going to write this down. Acceleration is the only link between kinematics and dynamics. Okay? It's the only link. So if you don't have the acceleration and you want the mass or the net force, you're going to have to use kinematics first to find it and then put it here so you can find the other unknown. Or it could be that you've got the force and the mass and you want the initial velocity, but you don't have the acceleration. So you use the dynamics to get the acceleration and then put it over in the kinematics and find the unknown there. Now, the definition of acceleration is not the only kinematics formula we have, if you'll remember. We also have the general equation and the alternate equation. And just like this one, they both contain acceleration, so they can link with the dynamics to help us solve problems. All right? Okay, so before we go any further, we're going to be practicing using the second law with our kinematics to look at change in motion. All right, we'll be linking them. So think about that, all right? And I'll talk to y'all later, and we'll do the third law with the next set of notes. And have a good day. See you soon.